Assalamualaikum and salam sejahtera. We are from Set 1, Group 5, are going to present about the production of formaldehyde. Introduction. So, formaldehyde with the chemical formula of CH2O, also known as the simplest aldehyde. Due to the solubility of it in water, it also known as formalin, where the composition of formaldehyde is 37%. It also being kept as liquid because it will be a poisonous gas. The usage of formaldehyde. One, it has disinfect property, where it is suitable to sterilize medical equipment. Second, it also used as preservative in cosmetic. Third, it also mainly used as precursor compound, such as for resins and also polyfunctional alcohol. Okay, the graph shown is a supply versus demand curve. As you can see, the demand line is higher than the supply line. And also, we're plotting this graph by using the CAGR of 4.9%. The shifting of CAGR from 5.1 to 4.9 due to the pandemic of COVID-19 that happened in 2020. As you can see on the slide, the supply and demand of formaldehyde will be keep increasing from 2018. As for the supply, we expect it will be increased around 40% in 7 years, where we predict we will have around 63.8 million tons in 2027. And as for demand, the roughly increase to around 38% in 8 years, where we expect the wood price of formaldehyde will be around 5. The price of formaldehyde with the CAGR of 5.1%, we predict that the price globally formaldehyde will worth around 36.61 billion USD in 2027.
There are several companies that produce formaldehyde, which are Hexagon Incorporation, which is located in USA. They produce 216,000 tons per year. There are also a company that produces formaldehyde in Germany, which is called BASF SE. They produce 650,000 tons per year. We also have a local company that produces formaldehyde, which is located in Sarawak. Hexagon Sarawak Sdn Bhd Malaysia produces 82,000 tons per year. Global supply and demand in 2027 are estimated to be 63,737.24 kiloton and 69,213.67 kiloton respectively. Therefore, we can calculate the diffusion, which is 5,976.43 kiloton per year. We decided to operate for 8,400 hours per year. Therefore, in our plant capacity, we will only produce 5% from the total diffusion. Therefore, we can get the plant capacity is 22,600 kg per hour.
We now look into our process flow diagram, which is on the production of formaldehyde. For our process description, the reaction occurs at the packed bed reactor R101, whereby the process is called vapor phase oxidation. It operates from 300 to 400 degrees Celsius and the pressure of 1 to 2 bar. The raw materials being methanol and oxygen gas react with each other with the support of a solid catalyst called molybdenum 4 oxide in order to form our main product, formaldehyde, and also our byproduct, water. As you can see for stream 3, it is the inlet feed for methanol, whereas stream 7 consists of oxygen gas. The effluent stream for R101 is cooled to 70 degrees Celsius and then supplied to S101 through stream 9. Water acting as solvent is also added to S101 through stream 10. Then, after the process occurs, off gases are released at the top of the S101. Next, the formaldehyde-rich stream from S101 is then pumped to the distillation column S102 through stream 14 in order to remove any remaining unreacted methanol at the overhead and also to reach the highest purity of formaldehyde possible at the bottom. The fractional recovery of methanol at the overhead distillate is 99.7%, while the fractional recovery of water at the bottom is 99%. Also, unreacted methanol and some traces of water will be released through this overhead stream. Lastly, at M101, the mixer, the stream 21 containing formaldehyde and water from distillation column mixed with stream 22 containing deionized water to form 37% of formaldehyde and 63% of water.
For the mass balance, since the methanol conversion is 99%, the rate of reaction is calculated to be 405.74 kmol per hour, and by using the formula of N out equals to N in plus alpha R, the component balance are calculated as shown above, while the mass balance on other unit operations are all balanced as well.
For energy balance, firstly at our reactor, which is R101, we calculated the standard heat of reaction at the reference temperature of 298 Kelvin, which is equal to negative 155.8 kilojoules per hour. Then we calculated the energy Q, which is negative 1.43 times 10 to the power of 7 kilowatts. Since Q is a negative value, this means that it is an exothermic reaction. Hence, heat is released from the system into the surroundings. Next, we look into the energy balance of other unit operations. For S101, which is our absorption column, the Q is negative 231.63 kilowatts. As for S102, which is our distillation column, the Q is equal to negative 4.23 kilowatts. And lastly, for our mixer, which is M101, the Q is negative 544.4 kilowatts. What we can conclude for all these three unit operations are that they are exothermic processes. Hence, heat is released from the system into the surroundings.
Next, we will move to safety procedures. For safety procedures, we will focus more on formaldehyde. Safety procedures, we will divide it into three, which are fire, leakage, and exposure. For fire, formaldehyde can cause explosion. Thus, when this happens, we have to contact firefighter immediately and cool the tanks with water. For leakage, formaldehyde can lead to serious health implications. Thus, when a leakage happens, we need to mark the danger area and please do not breathe any gas, fumes, vapor, or spray. Excessive exposure of formaldehyde can lead to serious health implications. Thus, when eye contact happens with formaldehyde, we have to rinse it immediately. When skin contact happens, we have to wash the area immediately. And when ingestion happens, we have to rinse the mouth with water. Formaldehyde has its own way to be handled and to be stored. There are several main points that we need to focus. To handle formaldehyde, the formaldehyde needs to only be used under fume hoods, and the person who handles it needs to wear personal protective equipment, which is PPE. Formaldehyde also needs to be kept from any source of heat and only can be used with non-sparkling tools to avoid any explosion. To store formaldehyde, the formaldehyde needs to be kept in a container tightly closed in a dry, cool, well-ventilated place, and it needs to be kept away from heat and source of ignition.
Now, I'm going to present about environmental issue, mainly on waste treatment. Waste gas that consists of air, water, methanol, and formaldehyde are released at stream 11. The waste gas is treated by using biofilter to remove the presence of low concentration of methanol and formaldehyde before release the gas to the atmosphere, while wastewater that consists of water and methanol are released at stream 19. Since the concentration of methanol is low, the methanol are removed from wastewater by using municipal activated sludge. The Environmental Act for this is Environmental Quality Act 1974 Act 126 under Section 33.
In this part of chemical reaction 2, we will talk about the selection of process, selection of raw materials and reactor, and also the catalyst. And lastly, we will talk about the rate determining. For the selection process, the production of formaldehyde are made by the process of oxidation, and there is three ways of using this method. Okay, first is the oxidation of methanol with silver oxide catalyst. Second is the oxidation of methane and other hydrocarbon. And third, which is the process that we bake, is oxidation of methanol with metal oxide catalyst. The raw material that involved in the reaction is methanol and air, because this is the most conventional and easier material to get, and this reaction will happen in a packed bed reactor because it will give a higher conversion rate. The selection of catalyst, there is two catalysts that we could pick. One is silver oxide and second is molybdenum oxide. Why we pick molybdenum oxide? It has a greater size. It also will give a higher conversion rate of methanol with 99%. It also has a high porosity where it will increase the reaction that happen in the reactor. The downside is it has a high utility cost where it requires more oxygen than silver oxide. But since our goal of reduction is to produce a high purity of formaldehyde, thus molybdenum oxide is the most suitable choice. For the rate determining, it shown on the slide where I will label the methanol as A, oxygen as B, formaldehyde as C, and water as D. And also in slide, it shows the rate expression of our process. In this model, we will use the bulk density of catalyst, 100 kg per meter cube. With this bulk density, we will get the constant that's shown in the slide. This is based on our reference of Sandhoop et al. In 2012. From this value and formula, we will be able to calculate the rate of reaction. As shown in the slide, the rate of reaction is 2 times bigger than the one that we use in the production. This is due to the bulk of density of catalyst, where I can conclude that the higher bulk density of catalyst, the higher value of rate reaction that will happen in the reactor.
For the separation process, the separation unit chosen is distillation column. This is because distillation column can separate unreacted methanol from formaldehyde water mixture, and also because the range between boiling point of methanol and formaldehyde mixture is high. In this separation process, methanol is the LK component, water is the HK component, and formaldehyde is the non-key component. The composition of components, operating temperature, and pressure are shown in this slide. Moving on to heat duty, the total reboiler heat duty has been calculated to be 4.27 times 10 to the power of 8 kJ per hour. Since it is a positive value, heating occurs and there is a temperature rise, while total condenser heat duty has been calculated is negative 7.2 times 10 to the power of 5 kJ per hour. The negative value proves cooling has occurred and there is a temperature drop. The mass balance on separation unit has been simulated using Symmetry software. Above shows the percentage error for the output value. The factors of this error are runoff error and default boiling point value on Symmetry is not the same as the value in the process plant. Next is type of tray. Sieve tray column is chosen because it is compatible with methanol formaldehyde water separation process. It is high capacity, high efficiency but low cost, low falling and low maintenance requirement. Next, shortcut method is used to calculate the minimum number of stages, the actual number of stages, the minimum reflux ratio and the feed stage location. By using Fensky equation, the minimum number of stages is calculated to be 8 stages. By using first underwood equation with Q equals to 0.6, theta calculated is 4.46032. And by using second underwood equation, we get R min equals to 1.2973. And because of reflux ratio R equals to 2 R min, we get 2.5586 for reflux ratio. By using Gillen correlation equation, the number of actual stage of R is 13 stages. The tray efficiency is calculated to be 63.4%, while for feed stage location, by using Kirkbride equation, the feed stage location is calculated to be at stage 6. Moving on, the diameter of this column is calculated by using this formula. It is calculated that the diameter of this column is to be 0.8374 meter. And lastly, for the height of the column, by using this formula, the height of the column is 8.712 meter.
Now, we move on to the plant design part. In order to simulate R101 on Symmetry software, we set it up through the reaction option, whereby we inserted the base component, its conversion, and also the stoichiometric coefficients of each chemical components involved in the chemical reaction. As you can see, the output stream of R101 is successfully simulated. After we simulated R101, we compared the result to the manually calculated values as shown in the table, and we find that the percentage error for the output flow rate of each component manually calculated are very minor. These errors are because of slight differences in decimal points. As for energy balance, the percentage error is only 6.0921%, and this slight difference is because of the CP in Symmetry are built in and of higher decimal points. Here, the simulation of the absorption column S101 is shown. Next, this is the simulation of the distillation column S102. Lastly, the simulation of the mixer M101 is shown.
Next, we move to chemical engineering computation. Algorithm is actually a series of steps that we need to write before we start writing the code. It is actually a very important step and it will make sure for our job to be easier so that we will not miss any steps when we start writing our code. Here are the algorithm for mass balance and energy balance. Algorithm can be represented in a figure form called flowchart. Any flowchart will start with start and ends it with end. All steps in algorithm then will be translated into flowchart. The flowchart is as important as algorithm as it will help the programmer to see the steps in algorithm clearly. Therefore, here is the flowchart for mass balance. Same with mass balance, the flowchart in energy balance will also start with start and ends it with end. Here is the flowchart for energy balance. Here is the output for the mass balance. As we can see here, the program will ask the user to enter the input mass flow rate for all the components, which are methanol, oxygen, nitrogen, water and formaldehyde. Then the program will calculate the output mass flow rates of all components. The input and output mass flow rates of all the components will then be presented in a table form. As we can see here, the total mass flow rates and the total mass flow for the input and the total mass flow for the outputs are balanced, which are 44,357 kg per hour. Therefore, there is a balanced message appear. Same goes to the energy balance. The program will ask the user to enter the molar flow rates for all the components, but here according to the streams. There are 3 streams total in R101, which are stream 3, stream 7 and stream 8. Then the program will calculate the Q, which we will get negative 14,276.75 kilowatt. Since we can see that there is a negative sign, therefore the whole reactions involved in R101 is negative. Therefore, the reactions is exothermic message will appear. For the numerical method part, we would like to find the temperature when the specific heat of water is equal to 75.3956 joule per mole Kelvin. Therefore, second method is used to solve this problem. Here we can see the equation that will be used to find the temperature. After we run the program, we will get the temperature is 297.993 Kelvin, which when we round it off, we will get 298 Kelvin. The value that we get from manual calculation, superput at MATLAB, will be compared with each other. So, after we compare, the percentage error between superput and manual calculation for the output mass flow rate for methanol is 0.53, for oxygen is 2.73, for water is 0.07%, and for formaldehyde is 0.03. Percentage error between superpro and MATLAB is the same as the percentage error between superpro and manual calculation because the program that we boot for MATLAB is solely based on the manual calculation. For the energy balance, the percentage error between superpro and manual calculation for the inlet enthalpy is 68.79%, and for the outlet enthalpy is 47.02%. For percentage error between superpro and MATLAB is also the same as the percentage error between superpro and manual calculation. In conclusion, 37% of formaldehyde in water can be called as formalin. Formaldehyde can be used as disinfectant and to preserve biological specimen. In terms of economy, supply has been increasing and does not satisfy the demand. And after we calculated, the plant capacity for this production is 32,600 kg per hour. For mass flow rates for both and inlet outlet is balanced with 32,600 kg per hour, same with our plant capacity. And for energy balance, Q that we get from R101 is negative 14,280.75703 kilowatt. Since the sign is negative, we can conclude that the reaction in R101 is exothermic. Reactor used in this production is a packed bed reactor. As for catalyst, molybdenum 4 oxide is chosen to be the catalyst in the reaction. So we can conclude that the bigger the bulk density used, the higher the rate of reaction. For the separation process, sieve tray is used as separation unit. The minimum number of stages is 8 and the minimum reflux ratio is 1.2793. Then we can get the reflux ratio, which is 2.5586. The number of stages N is equal to 13, and the feed stage location is located at stage 6. After calculated, the diameter for the distillation column used is 0.8374 meter and the height is 8.712 meter. For computer-aided plane design, a software called Symmetry is used to solve the mass balance and energy balance. Total output flow rate in R101 according to Symmetry is 44,357 kg per hour, and Q in Symmetry is negative 1.346 10 to the power 7 with percentage error of 6.0921%. And lastly, for chemical engineering computation, MATLAB is used and mass flow rates, inlet and outlets are balanced according to MATLAB, and Q in R101 according to MATLAB is negative 1.47 to 6.75 kilowatt. That's all from us. Thank you.